Hey there, calculus folks. I'm back here in Wolfram Cloud to give you another demonstration looking particularly at infinite series. If you remember in our last demonstration, we explored looking at sequences on Mathematica. We're going to now take that a little further and develop the case for an infinite series. Now, again, I showed you last time where you are going to want to go is to lab.wolframcloud.com. That will drop you into the login page for Wolfram Cloud. And if you want, you can sign up really quick and easy for a basic account, which is free and has very few limitations to it, folks. And then once in there, you might want to go ahead and just click into a new notebook. And as I had highlighted last time, you always want to name your notebooks because Wolfram Cloud does save everything that you do in the cloud here. So you don't want to lose your important stuff. So give it a name. We might call this the Infinite Series Demo, right? We can see this document has been renamed to an Infinite Series Demo. Now in the input line, I always like to work with code, folks. So I'm going to hit Alt 8, and that is going to think of my cell here for my input to be a version of code that Mathematica is going to run. And I always like to just highlight my code with these shaded cells under using the Alt 8 button. And as we saw last time, we aren't going to necessarily be able to look out to the infinite degree for our sequences and our series. That's going to produce some issues there with the infinite aspect of that. So we are going to be looking at sequences and series with some finite limitations on them, right? And we had looked at last time in developing the terms of a sequence using the table command and actually defining the arguments of our sequence as some explicit function of the index, and then using the table command to develop the n terms, or the number of terms that we're interested in that sequence. So what we might do here for the case of an infinite series, we are looking at summing the terms of the sequence given by a sub k. So we might start off by formally defining a sub k as a function of k, right, as an explicit function of that index k here, right? So what we might note is f of k underscore, right? This function here is our function notation. We are going to just call it function f, and then using this bracket with the independent variable k followed by an underscore is telling Mathematica we're going to treat this as a function. Now we are going to set it equal to the following operation or argument involving k. We are going to use set equal to, keep in mind, just so that we're not always, every time we hit shift enter, having this function given as part of the output of the code. So set delayed will actually hold on to that and not actually, it will hold on to it until this function is called, as opposed to always just evaluating f of k at this argument. Now we might go with a simple little argument of 1 over k squared to begin with, right? So this is going to be our function 1 over k squared, right? Now we saw last time that in Mathematica we can look at this as a sequence of values using the table operator. And we can apply that table operator onto function f of k, and we can consider developing this table for values of k, right, starting at a lower bound of 1 and continuing up through some upper bound. Now again, in a traditional infinite sequence, this would go up towards infinity, but we are going to put some limitations on this so that we don't build an infinitely long table. We might only consider this up through an index of 10, right? And we can note when we hit shift enter that will produce our output. Now, when you're initially evaluating cells, you will sometimes get this window. If you've come back into a program after leaving it, you will sometimes get this window. What I always like to suggest doing is just hitting the no button, right? If you do hit the yes button, what you will sometimes get is duplicate outputs. And to avoid getting duplicate outputs or two outputs for an input window, just go ahead and click no, right? And it still evaluates the cell. And what we can see here is we do get the first 10 terms of this infinite sequence, right? This sequence 1 over k squared. Now, again, it's not infinite. We are just carrying that up through an upper bound of 10. If we were to continue that and maybe consider evaluating it over values of an index from 1 to 100, we could also do that. And we do get the first 100 terms of this sequence. Now, let's keep this within limitation, and we'll go from 1 to 10 here. As we set up this demonstration. And the other thing we might consider as we set up this demonstration is that we are going to have to be adjusting, or we are going to want to be able to adjust these bounds in our exploration. And these bounds are going to be used quite a bit in our development here of a program. So we might actually want to declare these out as variable values. So we might call the lower bound in our sequence variable A, and we might call the upper bound in our sequence of values B, and we might say, well, let's consider the sequence from A equal to 1 out to B equal to 10, right? And what we will note is this does give us, right, the exact same sequence here, right? But we are going to be able to just adjust our boundaries A and B up here in the program, as opposed to everywhere that we see it develop in these tables and summations and such. All right. We had also seen last time that if we wanted to plot this table, we could certainly plot this out pretty quick. We would make, well, first of all, we'd have to make a table of values. Right. This time around, that would be thought of as a coordinate that begins at k, right? Well, a coordinate that has an x value of k, a horizontal value of k, and a vertical value of f of k. And we might consider developing this table of values again for values of k from a to b. And you can see this is where having those bounds of a and b are going to play out nicely. And notice that is going to give us the set of coordinates that we are going to see in our illustration, our plot. And we are going to then make a list plot of this table. Now, again, to make it a little easier here, I'm going to go ahead and call out this table as table T sub 1 and just make a list plot of that table T sub 1. And as we had seen last time, this is our plot of the sequence. All right. Now, the sequence given by 1 over k squared. All right. Now, to begin exploring the corresponding series of this sequence, folks, we could think of taking and adding up the terms of this infinite series. Well, careful, adding up the terms of the sequence up through the nth term, up through perhaps this 10th term. The way that we do that on Mathematica is we are going to do a summation, right? What we are going to sum are the values of f of k, right, over values of k, starting at the value of a and continuing up through the value of perhaps b, right? When I hit Shift Enter here, we do see that we get this one result right here. What this one result represents is the sum of the first 10 terms in this corresponding sequence. Now we could continue that out to the 100th term. Right? We would see that this would be the corresponding values in our sequence. This would be our plot, and this would be the result for that summation. Now, one thing I will note is that Mathematica is going to give you exact results, and when it can give you a rational answer to represent that exact result, it will do that. It'll do that both in the table here and in the sum of these first 100 terms. One way that you can turn these into decimal values, what I might do here, for instance, in this table, is I am going to consider turning this into decimal values by applying what we call the n operator to the table. If I apply the n operator to this table now, all right, and let me back it down here, back down to just 10. What you will notice here now is it does give us the sequence of values in their rational form, 1 through 1 over 100. But then it also, the n operator will turn those into a decimal value, right? We'll turn them into their decimal approximate. And it carries it out, that approximation out to a certain default level of decimal places. It appears to be 1, 2, 3, 4, 5, 6, 7. I do think we can change that, right? I do think we could change that to carry the decimals out to perhaps just 2 decimal places, right? And maybe we're looking at here 2 significant digits, right? And it does do that here in this particular case. Or we could carry it out to maybe 12 significant digits. And it does do that. What I like to do is just leave it as default, right? And we can get it out to several significant digits for each value. Now, we can also do that to these fractional values down here. I can take this sum, I'll go ahead and just copy it, and apply the capital N operator to that summation. And what we will see is that will then produce also the decimal approximate of this rational statement. All right? So that's a quick little way to get some number sense as to what the value of these fractions are. Or for instance, what would be the sum of the first 10 terms in this sequence, right? Certainly this fraction here is a little ambiguous in terms of some sense of how big that is. If we look at it as a decimal value, we can see it's about 1.55 in value, right? If we round out to 2 decimal places. Now, all we have here, folks, is the sum of the first 10 terms. We could continue, like I said, summing this out through the first 100 terms or summing this out through the first 1,000 terms, right? And see what that result would be if I could, for instance, sum this out through the first 100 terms again. And we would see that they add up to about 1.63 in value if we round out to just 2 decimal places, right? But what I might be more interested in is looking at the overall behavior for what we know as the sequence of partial sums. As we had noted, to begin exploring the behavior of an infinite series, we want to look at the corresponding sequence known as the sequence of partial sums. All I have here in this summation is just the last term in what would be that sequence of partial sums. What I want to consider developing here is a program that will sum up through the first n terms in that sequence. So to do that here, folks, I am going to develop a table, right? Another table here. Ooh, I'm missing something. Okay, let me close this out. What I want to bring up is actually, I'm going to look over. Okay, yeah. I want to make a table of summations here, folks. What I'm going to consider doing down below here is I am going to make another table for my sequence of partial sums. And what I am going to do is table up some summations, right? Summations given by the value f of k, right? Where, let me just double check here. Yeah, we're going to consider summing over values of k from 1 up through the value of n, right? This is going to form our sequence of partial sums up through the nth term of our infinite series, right? We are going to then want to think about this table forming over values of n then that begin at our lower bound, and this is where I should maybe make some adjustments. Let's consider this starting at a. We want to keep consistent with these bounds of a and b, and we are going to sum up through n values starting at the value of a up through the value of b. Now I do believe when I hit enter here, shift enter, there we go. Yes, we can see that what we produce is a another sequence. This is known as our sequence of partial sums in the problem, folks. And in fact, if we wanted to call that out, we could print here the following is the sequence of partial sums. All right. We go down there and it'll just take note. Here is our sequence of partial sums down below here. All right. So, folks, we could carry that out to the 100th degree, right, and see how this is behaving. But what we're really going to benefit from maybe is putting this into a bit of a plot, kind of looking at this as a plot of a sequence, very much like we had developed this plot of a sequence up here for just the terms that we find in this infinite series. Now, to make this into a plot, I am going to have to make a table of coordinates. So I am going to go back and make a table of now coordinates. The coordinates we're going to use here, let me double check my example here. Yes. Okay. The x-coordinate in this table of coordinates is going to be given by the value of n, whereas the y-coordinate is going to be given by the value of f of k. Right? Where, let me double check here. Careful there. Not f of k, it's actually going to be given by this summation above. Right? It's actually going to be, the y-coordinate is actually going to be the sum of f of k over values of k from a to n. Right? Where, let me go back and look at my example here. Oh, we are now going to then come back and form that table. Right? Much like we did the table above, considering forming it from values of n that begin at a and continue up through the value of b. Now when I hit Shift Enter here, we will get our sequence of partial sums, but then we will also get the coordinates that are going to become points in our table or in our graph for the sequence of partial sums. And now if I go back and I call this out as a table, right? Maybe we call this table 2. Not that one. We're going to want to table this up as table 2. Right? We can then come back and say, let's make a list plot of table 2 now. And what this will plot out is the sequence of partial sums as a plot of a sequence here. As we can see, unlike the terms do converge on the value of 0. We do see that these terms are growing in value. But what we might end up finding is that growth that we see in the sequence of partial sums could be what we call convergent behavior or divergent behavior. That is going to be some of the rest of the semester is going to involve exploring that. But what we do have is a nice plot of those terms. Now, some things we might add into this here just to help distinguish some things. First of all, we might, is there anything we want to get rid of? Let's get rid of this sum through the nth term. We don't necessarily need that. Let's get rid of the decimal approximation of it. Let's just look at forming a program here for the actual graphs, right? Let's put together the graphs for these sequences. Now let's see what this gives us. Okay, there. We do have our terms of the sequence that are going to be added up through the 10th term. We do have their decimal approximates. Maybe we go ahead and just get rid of those decimal approximates for now. We aren't going to need those. All right. And let's see here. What do we have then? Okay, so what we're left behind with now currently is our sequence of terms that we're going to be adding up. We do have their plot. and then we have their corresponding sequence of partial sums, what we get when we start to add up the first term to the second term. That's 5/4. The first three terms, that's 49/36. The sum of all 10 terms here will add up to be the last ratio found here in the sequence of partial sums. And what we do have is their plot now, right, as a plot of a sequence. One thing we might consider doing is combining these two plots. So let's go in here and let's make this plot style for the sequence. Maybe we make that red in value, right? And let's come down here and make this plot style blue, right? Let's stay with the traditional blue. Now, we will see that. Oh, what did I do wrong here? Oh, da 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 da. I put this in the wrong place. This needs to go into our actual plot, not into the table. Let me fix that, folks. Take that out of there. These actually need to go into our tables. Or, sorry, not in our tables, into our actual plots. And that will produce our red plot and our blue plot, right? We are going to then combine, perhaps, these two plots, right? One of the ways we can do that is we call this out as plot 1, the plot of the initial sequence. And then our sequence of partial sums plot, we might call that out as plot 2. And then what I can come down here into my last command and make it a show command. Apply the show operator onto plot 1 and plot 2. And what that will do is plot those two plots together. Come on, Mathematica. What happened here? Why did you crash? Oh, duh. It did not crash. It is going to produce our two plots here, but it is borrowing the plot range from plot 1. And plot range is 1 is automatically setting it so that we cannot see plot 2 in the picture. So one thing I could do is I could come down here and make my show have its own plot range, right? And what I said is a nice plot range for sequences that are non-alternating is to set a plot range from 0 to automatic. And there we should get a nice illustration that begins this range along the y-axis starting at 0 and then automatically sets an upper bound based upon the two plots seen in our picture, right? So we will go ahead and set that as our plot range there. And notice we do have both illustrated together. I did lose their individual illustrations. If I wanted to go back, this is the set delayed option, folks. If I remove the colon from the plot titles P1 and P2, that will return to us now also plot 1 alone and plot 2 alone, and then combine them in our final plot. What we might want to also do here is put on some labels onto these axes. For example, our show axes, we might want to label our axes label. Now, these represent a couple of different things. The x-axis represents either the k-axis in our initial sequence, or in our sequence of partial sums, it's going to be thought of as the n-axis. Whereas in the vertical axis in our combination of two plots, this is either going to be the plot of what we might call f of k, right? Function outputs for f of k, or we're seeing the outputs for the sequence of partial sums up through the nth term, right? And if I hit shift enter now, we do see that we get some nice labels on these axes. We're either illustrating k for our initial sequence and the plot of f of k, right? Or we're seeing, right, the plot for n from our sequence of partial sums here, and our sequence of partial sums being tracked along our vertical axis with respect to n. That is the blue plot. Now, to make that a little clearer up in here, we might go ahead and add these axes labels specific to these two plots. For instance, here, I am going to say that this is labeling out n and s of n, right? And in this plot up here, we are going to label out k and f of k on those axes individually. All right? So we get some nice axes label on each of these plots, and then the combination of the two axes labels seen here. Now, you might be looking at this plot going, are we missing a red dot? Right? If I go up here and I look, there is a red dot that is missing for the value of 1. We don't see 1 up here. In fact, if I was to go up here and set this plot range to be 0 to automatic, I do think we will see that. No, we don't see it. Let's go a little higher with that. Let's go up to the value of 1.5. Oh, careful there. What did I do? I got to go over here. Let's take out automatic. Let's make that 1.5. What is going on? Oh, I know what's going on. I'm using the number pad, and it doesn't have the number lock on. So if I go there I do see that one value that's occurring there at 1. We don't see it in the combination graph. It's not right here because it's actually being covered up by this blue dot. One of the things I could do in this list plot is to actually make my dots a little bit bigger than the blue dots, so that when they are combined, I will see the red dot hidden underneath this blue dot here. That is involving a plot style. To make more than one plot style, we are going to use what we call a directive command. We are going to have a directive here, right? Which basically tells the Mathematica program that we're going to want to have a couple of plot styles with the following order of importance for application. We are going to be using a red style where we're going to want to maybe consider adjusting our point size. Right? Making that point size something a little larger. Let's see here. If I go 0.1, is that too big? Yeah, that's way too big in terms of point size. Let's back that off a little bit. What if I go 0.01 in size? That's a little too small. Maybe we bump that up to 0.5. Now that's a little big. Let's go down to 3. Not too bad. Let's knock that just down to 2 and see where we're at. That's a little better. Right? What we do see there then is I'm just adjusting the point size so I can see this initial point here. This point where both the sequence of partial sums S sub n starts at the value of 1 and where our corresponding sequence starts at the value of 1. That wasn't so obvious initially here because the blue dot was covering up the red dot. Now it will show up nicely in our plot. We'll see that both the sequence of partial sums and the initial sequence f of k both start at the exact same location. And what we're doing here to go from here to here in the blue graph is we are adding on this value seen in the second plot to this first plot. Right? And then we add on this value seen at the third plot to that result to get to this plot, and so forth. All right? That becomes a little bit more obvious in our illustration. I was going to see, is there anything else that we want to maybe highlight here? I think that is it. I think that gives us a pretty good illustration of a program. What we might consider doing, though, is maybe we make this image a little larger. You can always adjust this image size. If I go down here and say image size as a command, so let's make that large. Large is a way of declaring an image size. And we do get a kind of a rather large picture there for that sequence of partial sums. Yeah. And some other commands for image size, you certainly could come over here and do a little search. There's some different options for image size. All right. And it will say, okay, here's image size. Here's some details on image size, right? The following changes can be given, right? You can talk about a width. You can say up to S, explicit width and height, right? We could say automatic, tiny, small, medium, large. As you can see, I use the command large, right? There are all these different commands that are possible with descriptions here down below, folks, in terms of using those commands. So, again, that is just working here in the search toolbar, looking at Each and every one of these commands that we use can be searched up in terms of its properties, right? We could look up sums, right? What does it mean to be a summation here? There's a bunch of different ways to form a sum. I think we went with this format right here, right? We declared our function f and then summed from the index of I, from this minimum index up through this maximum index. This automatically defaults to a step of 1 each time, a change in I by 1. If I wanted to declare my change in I could actually use this option here. All right. Then there is some details given below, right? There's all these details and these other possible options that I could include with the use of this command, right? Take note. And then they do give some examples down below, some basic examples, and then there are some even more complex examples, which they lay out underneath scope, where they do show you what is kind of the limitations and what are some of the extreme bounds that you can use this command with. Some other options, some more applications, and then just even other related operators that you can use in the program. All right, folks. This is our second demo here, where I did want to demo out infinite series for you. We can use this little demo to now explore infinite series. For example, here, this does produce for us this series 1 over k squared here, which does have this behavior here where I said we can look at series, and infinite series are going to behave one of two ways. With this behavior here, it might be divergent. It might be heading off to infinity along the vertical axis, or maybe it is convergent. Maybe this behavior is converging on some value found along this vertical axis, right? If I was to change, instead of taking 1 over k squared and just look at 1 over k, that produces this corresponding series, right? This would be the sequence of partial sums up through the first 10 terms of that series, and this would be the graph for that sequence of partial sums. Certainly, if we look at the combination of the two graphs, they look kind of similar to the case for 1 over k squared. We do see the terms of the initial sequence for f of k, the red graph, converging on this value as 0, but we might see a little different behavior in how that sequence of partial sums behaves here. All right. This program is going to allow you to start to analyze and different cases for infinite series and be able to take them out to a pretty extreme degree. For instance, I could calculate this out to the 100th degree. All right. This would be the illustration of just the corresponding sequence or the terms in our infinite series, right? These would be the terms seen in the sequence of partial sums, and you can see it's going to tell you all 100 of those if we don't remove that, right, from the output. Now, what we do then end up seeing are the two graphs here. We have our sequence of partial sums plotted out this way, and we have this corresponding graph combining the two illustrations. And it is nice that it does show us, right, the two graphs out to the 100th degree. And notice this graph's behavior, right? As we go out to the 100th degree, it's now up to the value of 5. Right? If we go back down to the 10th degree, right, if we go back to the case for the 10th degree, right, it seems to be around the value 2.53 in value out to the 10th degree. It does appear to be growing, right? If we were to take this out to the 1000th degree, now one thing I might do here, because this is going to get quite rather large in our tables, let me go ahead and make this so it does not show this table, and I can do that with a little semicolon. It'll exclude these results if I put a semicolon behind them. And then let's consider just making these plots out to the 1000th degree and see what happens here. Here's our initial plot out to the 1000th degree. Here is our sequence of partial sums out to the 1000th degree. And we can certainly see that it is growing still. At the 100th degree, it was around here at 5. At the 10th degree, it was around here at 3. And now to the 1000th degree, it's more than 7 in value. Right? it does appear to be illustrating some growth. Whereas if we go back and we look at something like 1 over k squared and its behavior out to the 1,000th degree, right? Notice the illustration of the behavior. All right, this would be our initial sequence. Here is our sequence of partial sums. And notice it does grow initially, but with respect to n, right, as n gets larger, it does appear not to grow very dramatically. In fact, it looks like it could actually be a convergent behavior. It's not any larger than a little bit more than 1.5, maybe 1.6 here in value. Right? That's true for out to the 1,000th degree. Let's see, at the 100th degree, it does still appear to be heading to right around this value, 1.6 perhaps. And we can even take that down to the 10th degree. All right? Over those 3-degree changes, we don't see a very dramatic change in the output of the sequence of partial sums, right? In the terms seen in the sequence of partial sums. They do grow, but do they grow divergently? They don't appear to, right? Not like 1 over k, right? If you go back and you look at the graph of 1 over k, you will see that it does appear to grow rather divergently. Right? So that is one thing that this demo is going to allow us to do, is to kind of explore this behavior for these different series. Be able to compare something like 1 over k's growth to the growth of 1 over k with respect to n. Right? With respect to n, this does grow up to a little bit about 3 when n is 10. If we were to continue that out to 100, certainly gets a little larger if we were to continue that out to 1,000, right? We can certainly see it seems to be growing without bound, right? It's now above 7. If I was to continue this out to maybe, do we want to do it 10,000? Can Mathematica handle it? It can handle it. Come on. Where's it at? We are putting a little stress on the system here, folks. It is having to add up, right, up through 10,000 options here. Let's see if it can get there. It may have stalled out on us. It says it's still calculating. Right? Did it give us anything? No. Sometimes it will lock up like this, folks, and this is probably a good thing. Let me go over here and show you this evaluation window. You can abort evaluations in this window, right? I can go ahead and just abort that evaluation, right? So what's going to come up here is not going to crash on us, right? I can actually go through and delete all output. That's sometimes nice if you're running into some bugs in your program, or if you have an error start popping up that you don't know where it came from. What I always suggest is maybe deleting all your outputs, and then when sometimes starting new with the program here, you sometimes want to quit the kernel. What the kernel is, folks, is it stores all of these variables in its memory, and it's what's called its kernel. And if you want to completely flush the kernel of all its memory, flush the entire memory of the program, what I suggest doing is deleting all your outputs and quitting your kernel, especially if you're running into some errors as you run that program. Now, I did run this out to the 1,000th degree. Maybe we just carry it out to the 10,000th degree. Let's just go out to the 2,000th and see if my Mathematica can handle that. All right? This is going to take a little bit of time here. Oh, there it does. It can handle it. Keep in mind, it had to add up 2,000 items after adding up 199, after adding up 1,999, after adding up 1,998 items. But you can see here, this output for the sequence of partial sums does still appear to be growing. It's now about at the value of 8, all right, in value. So again, we do see maybe some divergent behavior in this quantity 1 over k, especially when compared to 1 over k squared. Right? If we go back and we look at 1 over k squared, again, this takes a moment, we've seen, but it can handle the 2,000th degree, right? Notice, again, it's not much bigger than 1.6 in value, right? there does appear to be some convergent behavior happening in this particular series. All right. So that's just a quick demo over infinite series, folks. This is the program we developed. You can go through and develop this program for yourself in Mathematica, and you can use it to kind of study your series, folks. I hope this all helps. I'll see you in the next video.